In electrostatics, we can calculate the electric field using three different ways. One is using Coulomb's law, okay, that is most generalized form, and the second one is using Gauss law, okay, and the same can be computed using the potential called as electric scalar electric potential V. Okay, so E can be calculated using three different ways. Okay, the equation which relates electric field density E vector to scalar electric potential is E vector is minus del V. E vector is minus del V. Similarly, we can form an equation which relates magnetic potential with magnetic field density. Okay, the potential may be a scalar or a vector. The scalar is denoted using V with a subscript m to differentiate it from electric potential, and a vector a vector. Okay, so using the scalar magnetic potential Vm, we can form an equation H vector is equal to minus del Vm minus del Vm. Okay, and the unit of scalar magnetic potential is amperes. Okay, so H vector will be amperes per meter. We know the point form of Ampere's law, that is J vector is del cross H, and just replace this H with minus del Vm. So J is del cross minus del Vm. Okay, but as per vector identity rules, the curl of the gradient of any scalar field is equal to 0. Okay, so this one becomes del cross del, so this one must be 0. So the scalar magnetic potential Vm is applicable only when the J vector is 0, otherwise it's not applicable. So the scalar magnetic potential can be defined in a region where J is equal to 0. Okay, del dot B, we know the equation del dot B is equal to 0, where B is mu naught H. Just bring the mu naught outside. So mu naught del dot H is equal to 0. So del dot B is equal to mu naught del dot. Instead of H, just substitute minus del Vm. So mu naught del dot minus del Vm is equal to 0. So from this you will have del square minus del square Vm. Okay, in front of that you are having minus mu naught, that is equal to 0. Now bring the quantity to right side, you will have del square Vm is equal to 0. This equation is applicable only if J vector is equal to 0. Now let's see the magnetic potential that is in vector form. Let us consider the magnetic flux density B vector. Okay, the divergence of magnetic flux density is always equal to 0. That is the Maxwell equation. Del dot B is equal to 0. Okay, let's define a vector whose divergence is 0 can be expressed in terms of curl of another vector. Using this property, we can define the flux density B vector is equal to del cross A, where A vector is the magnetic vector potential with a unit bus per meter square. Using the vector identity del dot del cross A is equal to 0, I mean the divergence of curl of any vector field is 0. Okay, using that we have formulated this equation. Now let's take the biot-savart law and let's try to derive the vector magnetic potential A vector from the biot-savart law. The biot-savart law for a current carrying filament. Okay, let's take the observation point P, okay, which is at XYZ, and here is the filament conductor, and the differential element is that X dash Y dash Z dash, and it is observation origin, and from the origin to element it is R dash, the origin to observation point is R, and the distance between these 2 points is R minus R dash. Using this, you can define H or B, where B is mu H, so B is mu naught I by 4 pi line integral of dl cross R by R cube. This is the biot-savart law, where R is the distance vector from the line element dl dash to the point, okay, from x dash y dash z dash to x y z. So r is the magnitude r is x minus x dash square plus y minus y dash square plus z minus z dash square power 1 by 2. We know that del of 1 by r is equal to minus r vector divided by r cube. Okay, you can derive this. Okay, so using that property, you can change equation 4 into b vector is mu naught I divided by 4 pi line integral of del of 1 by r cross dl. Here the negative symbol is removed by interchange in terms of vector product. Considering the following vector identity del cross f, where f is scalar and f vector is vector, f del cross f plus del f cross f. Okay, using this you can form equation 6 as del of 1 by r into dl is del cross dl by r minus 1 by r into del cross dl, and del cross dl is 0. Okay, so substituting that, you have b vector is mu naught I by 4 pi line integral of del cross dl by r. Okay, so by rearranging the term, b vector is del cross mu naught I by 4 pi line integral of dl by r. Since b is del cross a, which we had in the starting of vector magnetic potential, comparing these two equations, you can define b vector, a vector is this part mu naught I by 4 pi line integral of dl by r. Okay, and we know that b is del cross a. Okay, and the magnetic flux psi is equal to closed line integral of b dot ds. Okay, so instead of b, you can substitute del cross a. Okay, if you do this using Stokes theorem, you can convert this one into line integral of L a dot dl. So psi is equal to closed line integral of a dot dl. Okay, so from the vector magnetic potential, you can calculate the magnetic flux density, or directly you can calculate the flux using dot product of the magnetic vector potential. Okay. So if the current carrying conductor forms a closed loop, the above equation can be written as A vector is mu naught I by 4 pi line integral of dl by r, and the vector magnetic potential for surface is, you can replace dl by ds at the time mu naught I by 4 pi surface integral of k ds by r. For the volume integral, A vector is mu naught I by 4 pi volume integral j dv by r. Okay, so you can apply the magnetic vector potential to line integral, surface integral, or volume integrals. Okay, and now let's have some examples based on the vector magnetic potentials. Show that the vector magnetic potential due to moving charge q at a distance r is given by a vector, that is mu naught q u vector divided by 4 pi r, where u vector is the velocity of charge. Okay, so the vector magnetic potential due to a line current is a vector, that is mu naught by 4 pi line integral of I dl by r. Okay, here you can take the constant outside, so mu naught by 4 pi r line integral of I dl. Okay, we know that I is the rate of change change of charge, so I is dq by dt, and the velocity is rate of change of distance, so u vector is dl by dt. From this you can write dl is u vector cross dt. Okay, and I is dq by dt. So by substituting those two in the equation 1, okay, so dq by dt, u vector in dt for the ideal. Okay, you can cancel dt. Okay, so mu naught u by 4 pi r integral dq, so integral dq will be q, so the unit is Weber per meter, so a vector is mu naught u by 4 pi r q Weber per meter. Let's see the second problem. Given the magnetic field, vector potential a vector is minus rho square by 4 az vector Weber per meter. Calculate the total magnetic flux crossing the surface at pi equals pi by 2, with rho is from 1 to 2 meters and z is from 0 to 5 meters. This problem can be solved using two ways. The first way, we know that B vector is del cross A. Okay, So A is given, first we have to calculate B, then by integrating B with respect to, by taking a divergence of B, can get psi. Okay, so del cross A, AX, A rho, A pi, AZ. Okay, you are having 1 by rho here, 1 by rho here, rho is by here, dou by dou x, dou by dou rho, dou pi, dou z, and 0, 0 minus rho square by 4. Okay, so using this, if you solve, you will get b vector is rho by 2 a pi, and the vector which is coming the surface out of the surface is a pi with the values d rho dz. Okay, so just substitute b vector and dcs here. Okay, so what you will get, rho by 2 a pi vector dot d rho dz a pi vector, just you can cancel, so rho by 2 d rho dz. Okay, so you will have 1 by 2 outside, rho square by 2, which is having the limits 1 to 2, and z is having the limit 0 to 5. You substitute the values, you will get 15 by 4, that is 3.75 Webers per, 3.75 Webers. Method 2, you can use psi, that is equal to closed integral of a dot dl. Okay, I mean flux of each and every lines. Okay, so here the path L is bounding the surface. Okay, this is the surface. Okay, and the path covers this entire thing. So you are having 4 different sections, and each and every section is having its own flux, psi 1, psi 2, psi 3, and psi 4. Okay, so here line segment 1 and 2 having the component along y-axis, and since A is having only z component, okay, it's having only components along z. Okay, you can tell the psi 1 and the psi 2 is 0. There is no component along y-axis. Okay, along y-axis, since it is having only z component. And the now if you substitute psi 1 and psi 3 is 0 in equation 5, you will get psi 2 plus psi 4. Okay, that is 1 by 4 into a dot dl. Okay, so 1 square 0 to 5 dz plus 2 square 0 to 5 to z dz. Okay, if you solve this, you will get 15 by 4, that is 3.75 Webers. Okay, let's have the third problem. If plane z is equal to 0, carries uniform current k vector is ky ay vector, obtain magnetic field intensity. Consider the current sheet shown in figure. Okay, so here this one carries a current k. Okay, and the observing element is at x dash y dash 0, it is along, it is at the z equals 0 plane. Okay, and we are observing the field at point P at 0, 0 z. Here we know that for surface current distribution, the vector potential is dA is mu naught k ds by 4 pi r, where k is ky ay and ds is dx dash dy dash for z greater than 0. Okay, and r is 0, 0 z2 minus x dash y dash 0. So if you take the r, you will get this, and where x dash are source coordinate and the x y z are field coordinates. Okay, and by substituting 3 in 1, you will get dA is mu naught ky dx dash dy dash ay divided by 4 pi into x dash square plus y dash square plus z square power 1 by 2, that is dA. Now we know dB is del cross A, B is del cross A, so dB is del cross dA, that is minus dou by dou x of dAy ay. So just substitute that, I mean take an x differentiation of A, you will get dB. Okay, so you will get mu naught ky dx dash dy dash ax divided by 4 pi into x dash square plus y dash square plus z square power 1 by 2. Now b vector is integral of this. Okay, so take the constant outside, so mu naught kyc ax divided by 4 pi integral minus infinite to plus infinite, integral minus infinite to plus infinite. This one is for x and y, the remaining quantities. Okay, we can change the integral from Cartesian to cylindrical for the simplicity. If you do this, rho will be from 0 to infinite and pi will be 0 to 2 pi, and this one changes like this. Okay, and after solving you will have b vector is mu naught ky ax divided by 2. So you know that b is mu h, using that h is b by mu naught ky by 2 ax. Okay, for z greater than 0. For z less than 0, simply change the ax by minus ax. So you will have the magnetic flux density, sorry, magnetic field density. H vector is ky by 2 ax for region z greater than 0 and minus ky by 2 ax for region z less than 0. I mean, above the surface you will have ky by 2 and below the surface you will have minus ky by 2. Okay. Now let's see the applications of magnetic potentials. Okay. Scalar potential. If the current carrying conductors occupy small fraction of a region of interest, then the scalar potential is more useful. Okay, so problems which involves permanent matters can be solved using scalar potential. The only limitation for scalar potential is the current density within the region must be 0. Vector potential, there is no such restrictions. Okay, and this one is more useful to solve radiation equations. Okay, radiations mostly occurs from antennas, apertures, leakages from transmission lines, waveguides, and microwave ovens. Okay, so to solve radiation equations, we are mostly relying on vector potentials. And here is a uh, analogy between electric and magnetic field is made. Okay, the basic law in the electric field is Coulomb's law and Gauss law. In the magnetic field, it biot-savart law and Ampere's circuit law. Okay, and here the force is QE, here force is Q U cross B, and the source element here dq, here IDL, and the field density is V by L here, here I by L, here plus density D is epsilon E, here mu H, here minus del V, here minus del Vm for j equals 0, and V is integral rho L dl by 4 pi epsilon r, and A is mu I dl by 4 pi r. The flux psi is d dot ds, here b dot ds, and psi equal to q, that is Cv in electric field, psi equal to Li in the magnetic field. From that you can get current I is C dV by dt and V is L di by dt. Flux density D vector is psi by S, or flux density B vector is psi by S. Energy density of dE in the electric field, of BH in the magnetic field. Poisson equation is del square V is minus rho V by epsilon in the electric field is, and in magnetic field it is del square A is minus mu J.